An overloaded function is a function that you can define once and then instantiate on different Haskell data types. Sometimes there are situations where you want a general behavior for a relatively large class of types, and then you want a more specific behavior for a subset of those types. And these are situations in which you can typically solve this problem by using overlapping instances. In this episode, we're going to look at overlapping instances, but also discuss some of their potential problems and discuss also a different solution, how you can encode similar programs.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed. We invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yes, okay. So the initial example I wanted to look at is sort of a re-implementation of the Haskell show function. Show is a type class, and there is a method that can take a value of some type to a string representation. And this is not exactly the same as the Haskell show class. I'll say something about this in a bit. But here, yeah, I just defined my own class, myShow, and a method, myShow from A to string. And I've already defined two instances for base types, for characters and for booleans, where I'm simply, to keep things simple, re-implementing myShow as the pre-existing show. And now I want to look at an instance for lists. Right? So I can define instance myShow A to myShow list of A. And how do I implement myShow on lists? I'm not going to do anything really fancy, so I'm starting with an opening bracket, and I need an argument. And then I want to show all the elements, right? So map show over access, and then I have a list of strings, and then I want to insert commas in between those strings, and then at the end.
Did you mean myShow there?
myShow, yeah. That's actually... You and GHC were complaining at the same time.
I'm faster than GHC.
Yeah, usually, yeah, okay. So, yeah, we can try this out. Right, so I can do something like myShow of, let's say, a list of booleans, false, true, false. And I get a string representation of this list of booleans, as expected. And I can also do myShow of, say, a string, which is a list of characters, Unfolder, let's say. And then I get it printed as a list of characters, right? But this is a typical situation where actually also in Haskell itself, the show class does something interesting in order to get strings, which are lists of characters, a different show instance or a show behavior as other lists, right? So how do we do this if we want to reproduce this ourselves? So one way to do this is to simply try to define myShow for a string instance, and then give it a different implementation. So here we would start with a double quote, which we now have to escape, right? And we also end with a double quote, which we have to escape. And in the middle, well, we can basically just put the string itself. That is not entirely accurate because, I mean, I guess the string can contain other double quotes, which we, strictly speaking, would have to escape yet again. But to keep things simple for the demonstration here, I'll do it like this. Now, if I try to run myShow on Unfolder again, so if I try to refresh this, I'll get an error message that says I have overlapping instances, because GHC is correctly complaining that there are now two instances that are both matching my argument. There is this instance for strings and this instance for lists. And by default, if you don't do anything further, GHC will complain about this. There is, however, a relatively simple way of telling GHC to do it anyway, and that is to annotate one of these instances with a pragma. And there are actually, like, I mean, two different ways. You can either mark this first one as overlappable or this second one as overlapping. So let's do one of these two things. And once we do this, we get the desired string representation for my show. And we still get the normal list representation for a list of booleans. So,
and it's picking the second instance because the second instance is more specific, right? That's something that, like, GHS has some sort of disambiguation procedure.
Yeah, exactly. Yeah, right. So for a string, it's still the case that both instances match, but exactly as Etsko is saying, the string instance applies because it is seen as more specific. Exactly. Okay. So before we discuss other options to do the same thing, I just very briefly want to go a little bit, not too much, into sort of like why one could dislike overlapping instances. I personally think they are generally fine, but they can be confusing in certain situations. And to demonstrate a little bit why that might be, you can imagine that, let's comment out this instance for the time being again, that we have a function called example, which takes us like a list, and then calls my show on the list concatenated with itself. And if we call my show on unfolder here, we get the original instance, because at the moment I've commented out the overlapping instance, right? And if I, sorry, I should say example, right? I mean, I should say example on unfolder. Then we get sort of like the concatenated version of this. And if we uncomment the instance, then as expected, we are getting the string representation. Okay, but what could be misleading or what could be confusing or surprising is that if we go to a different module and we move this instance here from here into this module, which is allowed, right? Because instances are like, I mean, I can define instances in different places. And so here we are importing show from the other module. We're defining the overlapping instance and we're calling example unfolder. And now we're not getting the string representation, even though that instance is defined. Right? And why is that? That is because if you look at the inferred type of example, I can actually just write that down. This is the inferred type that GHC gives it. It already applies the only instance that is in scope here, right? You can see that from the constraint being my show A. So we have a list of A as an argument, right? But then GHC already looks, oh, well, here locally, the only thing I know is that there is this instance, and it's the only instance I know about, and I can apply it. And so the only constraint I still need is this my show A constraint. And at that point, you have already ruled out using potentially later defined other instances. You can also see that if I remove the signature again and move the overlapping instance back into this module, the inferred type changes, for example, just by adding the instance. And suddenly, the inferred type of example is this, where we like have a list of A to string, but we have a my show constraint for list of A. So now GHC has not yet committed to using this first instance because it sees that these two instances are in scope and it might need further information in order to make the decision. And funnily enough, you can restore kind of the correct behavior also here if we explicitly give this uncommitted type signature, for example, and move the instance back into the other module, and now call example, then we get the string-specific instance again, right? But this is very subtle. And it is.
And in fact,
possible...
GG will warn you, right? When you define your by the default options, GG won't like that definition on line 20. It will tell you something about, oh yeah, you said my show of list of A, but actually there's an instance matching this.
Yeah, I don't have all warnings enabled. Let's try that. Okay, so that's about redundant imports. I'm not sure, actually. I think it's fine. I think it depends on some other things. I think there are certain circumstances. And I mean, obviously, this is also GHC 2021. There were, in the old days, in Haskell 2010 days, you need flexible contexts or so in the first place to even be allowed to write something like this, right? But yeah, let me disable WAL for the time being, because otherwise I always get these redundant imports, which I might need later. Yes. Okay. So that's one of the reasons why you might want to avoid overlapping instances. But we will hopefully see another example where there is yet a different reason why there might be a good reason to get around them. So I want to show a technique which actually can be applied, in my opinion, all the time. I mean, I haven't proved this or something, but I haven't yet found a situation in which I could not, if I wanted to, rewrite a situation with overlapping instances into something else. And that doesn't actually make it simpler. Actually, it requires more writing, but it has the advantage of getting rid of the overlap, right? So let me see if did I just lose my instance? Sorry. Let me get that back once more into the original module so that we have all the code available. And let's see what we want to do. The trick is, as the title of the episode also says, is to use a type family in order to make the decision between like whether we have the specific case or not, and to explicitly give up the idea that we can extend the class later, right? I mean, so that's another price you pay, but that's also something which in a way is good, because as soon as overlapping instances are involved, and a certain amount of closedness is actually good to keep control over what is going on. So what we can do is we can define one instance of my show for lists, one and only. Let me comment out these two original ones. And basically dispatch to a auxiliary class, which I'm going to call myShowPrime, which I have to define, with an additional argument where I'm going to basically make an explicit decision whether I'm in the first or in the second case. And I'm going to use a type family to make that decision. So in the simplest case, I can just, for example, say is string of list of A, and define a type family that computes a Boolean, let's say, true or false, a type level Boolean, depending on what the answer is. And then we still pass the original type as well. And the definition then is also going to be my show is simply going to be my show access, or is simply going to be my show prime access. Okay. So that's the idea. So we need the type family. Actually, let's start with the type family perhaps. So type family is string, is taking a type and is giving us a bool, and is string of string is true, and is string of anything else is false. And now I'm defining the auxiliary class myShowPrime, which takes a Boolean, and it takes, perhaps also explicitly say this is supposed to be a Boolean, and takes a type A.
So this is a type level Boolean, right? Just to be clear.
As a type level Boolean, yeah. And then that's why data kinds is enabled here as well as type families. And then my show prime is getting, basically an APA string again. And now we have one more problem to fix, which is like one of these typical inference problems. That so we have an overloaded method here, myShowPrime, but the class instance mentions B and A. And in order to infer what the intended value of B is, like the type of myShowPrime is simply not expressive enough. So we either need to use an explicit type application or a proxy or a mixture of both. And I always like to do this mixture of both, because by putting the proxy argument here, we're making it explicit, right, that we expect a type argument to be passed, right? So the only purpose of the proxy is to fix what the value of B is, and then here we also have to fix what the value of B is, and the value of B was supposed to be a string of A. Okay. And now I still need to define the instances, and the instances of my show, I mean, I can basically use these ones as a template here, so that this is the general case. So in the general case, I have my show prime of false, right? So that is if I don't have a string available, and I still need the my show a constraint, because I still want to show the elements, right? And that should go to the original class. And here I need to pick up the proxy, but I don't need to do anything with it. So the rest of the definition just goes through as previously. And here, in this case, I don't need overlapping anymore. I can say something like, my show true.
My show prime, I guess.
My show prime, thank you. And here again, I need to pick up the proxy, and that goes through. Now, first of all, I guess before anything else, we should figure out whether it still works. So let me actually, like even perhaps delete the old results, so that it's really clear that we are reevaluating. And so this still works. And oh, the other one was already done. Okay, like I mean, sometimes HLS is having like a weird semantics to refresh multiple things at once. So yeah, okay. So but yeah, it does work as expected. You might also think that, have we actually won anything? So is this actually so much better? Because like it still looks like we are having a list of A and a string here. But the point is now these two instances are completely separate from each other, because this one has a false here and this one has a true here. And in fact, the string isn't being used for matching the instance at all. I could even remove the string here and simply on the left-hand side put an A is equal to char, as we have been mentioning in one of the previous episodes of the Unfolder as well, that this is a common technique. Yeah, so this is the general technique that you can apply, right? I mean, and this really works in general. Like if you have an overlap, you introduce a type family that makes decision between the overlap. If you have a more complicated overlap between multiple different things, you may need to return something more complicated than a Boolean here that makes a decision between multiple different things. And then you dispatch to an auxiliary class that explicitly makes the or depends on the outcome of this particular test. Okay. Do we have any questions at this point?
Not so far, no.
Okay, good. Well, I mean, not good. I mean, I'm happy to happy to take questions as well, but I'm just going to assume that everything is crystal clear, so that's also great. So let's look at one other example, and so let's assume we want to write a flatten function, and flatten is a function in a class that takes an A to something else, to a different type. And this different type is actually not predefined, but it is itself defined via a type family, or in this case, an associated type defined within the class. So we can like say what we want to flatten something to is some form of simplification or removing some parts of the structure, but in an ad hoc way, and we say per type what we want to do. And I've given a base case here, so that, like, say we can flatten a Boolean to a Boolean, and then on Booleans it's just the identity function. And now we want to extend this. And what I would like to do is I would like to extend it in such a way that I can apply flatten to arbitrarily deeply nested lists, and then collapse all the lists together, basically concatenate, flatten all the lists so that I have a single list left. And the idea here is that I will start with a flatten list of A, where I do something like type flattened list of A. And here you can already argue, I mean, do you put list of A? But perhaps it is even nicer to put flattened of A here to basically allow a recursive call. And then, of course, we need a flatten A constraint up here. And then how do we do this? We get some excess. So we are simply mapping flatten over excess. Okay. So that is something that deals with a single list, but I now need something.
So far, if we have a list of Booleans, it
Yeah,
just gives you the exact same list of Booleans, right?
Exactly. If I have a list of, I mean, that is even intended, right? I mean, a single list of Booleans, yes, but also if I have something like a doubly nested list of Booleans, something like this.
Right.
Then it also keeps the structure. So it's only the
for here we
function,
would want
right?
a single list.
Here we would want to concatenate it, right? And so I might want to do an instance of flatten for lists of lists. And what I would like to say is that flattened of lists of A should actually be flatten of list of A. I simply want to strip the outer version. And then I would want to say something along the lines flatten of excess is something like concat map flatten. Right? Flattened, sorry. But at this point, I'm getting, I mean, there is another error in here as well, but we don't even notice it because the first thing that GUC is complaining about is it says conflicting family instance declarations. And it's complaining essentially about the overlap between these two type family instances. And that's like that has to do with the way that associated types are being translated by GUC. Associated types are essentially lifted. You can basically implicitly lift them out of the class and see it as an open type family. And all these cases are next to each other. And where there is this idea of that the more specific instance might apply for overlapping instances, that simply does not work for type families, for open type families. There is no way. And I cannot simply, like previously, say overlapping here. That will not resolve this particular error. And also,
so for type classes, we have some implicit ordering, right? Which is like if something is more specific than something else, it sort of takes priority. But that simply does not work. That simply is not implemented for type families.
Yeah. Now, one way to fix this would be to not just move flattened out of the type class, but also turn it flattened itself into a closed type family. And that sort of like is a little bit similar to the decision procedure thing that we have been doing. But in this particular case, it's not really desirable to do that because, like, while we're currently talking about lists, right, we might later still want to give flattened instances for for completely different types. I don't know, for trees, for maybes, for whatnot. And if we make flattened into a closed type family, we cannot extend it anymore. We have to go back to the original place and do all that logic in there. So it might be better to keep the open flattened type family and just deal with the list sub-problem in a different way. And that is where we can basically apply the previously seen technique again, right? So we can say something like type family is list. And again, this is applied to a type and is giving us a bool. And it's list of a list of something, I can even put an underscore there, is true, and its list of any other type is false. All right, so that is the preparation. And then again, I'm going to replace these two instances with a instance that says like just instance flatten list of A. And I'm going to dispatch here to flatten prime of islist of A in this case. I mean, I'm really interested whether the inner A is another list, yes or no. And I'm still going to pass the original type. And I'm going to say flatten of access is flatten prime of. And we already know now that we need this proxy argument. So of proxy of islist A of access. And then I need to define class flatten prime, which takes this Boolean and type A. And I have a flatten prime function here, which has a proxy B. And it takes an A to A. And now, well, what is our result type here? We don't have flattened now, right? Because it was an associated type of the original class, but we can just make another associated type here as well. Flattened prime, which takes the B and the A and gives us a Boolean from, and gives us a computed type from that. I'm not sure why I get this error. What is this? Flattened proxy is list of.
Oh, well, we need some sort of relation between flattened and flattened prime, I guess, the type families. Oh, no, you need to give it, no, you need to say what flattened of list of A is. In the definition of flattened, in this instance, you haven't gotten a definition of flattened yet.
Oh, yeah, sorry, exactly. Type flattened list of A is flattened prime of its list A. List of A. Okay. Right, and thank you. And then I can again start from the original instances. So this is the general case. So here I have flatten prime false, and I have flatten prime false, and I have flatten prime underscore, and then it works. And here I have the special case. So I have flatten prime true, list of A, and I have flatten prime true, this, and I have flatten prime this. And now I'm getting another error, which is actually true because, well, in order to be able to do this, we need to know that the result of flattening this list is actually going to be a list again. Right? Otherwise, we cannot concatenate the results. So if we map flatten over the list and we don't get a list back, then we are in problem. But we can simply require this. So we can say flattened. What was actually the flattened is list A. So what we need is that flattened list of A is a list of B, something like that.
And presumably also need to.
And we also need that. Oh, we also need that flatten of list of A. It's even possible.
Right. Exactly.
Yeah. Okay. But now it works. So now we get the right result. So
Very nice.
if I even add another nesting level, so if I like put another level here, don't want to write very much, so I'll simple. Oh no, now I've made a parser. Keep it simple was a good idea, but okay.
There you
but,
go.
in principle, it does work. Okay. I have one more thing that I want to show, which basically also perhaps illustrates the point that that this approach is powerful, or more general as well. Because, as I said, I mean, we could now think that we want to give an instance for maybe as well, right? So let's say we want an instance for flatten of maybe a. And there are multiple ways how you could do that, but one might think that, oh, well, one way would simply be to say the flattened maybe should also be flattened to a list, right?
Okay.
And that we say flatten of nothing should give us the empty list, and flatten of just x should give us a singleton list. Okay. And now if we try this out, and we do something like list of list, well, let's just keep it simple. A list of just 3, just 4, we get this. And that's not really what we want, but it is totally correct. It's totally what we've written, because we have said, well, we are making the decision based on the fact whether our input is a list or a list of lists. But that's not really what we want, actually, right? What we really want is we want to make the decision based on whether the flattened version of the A, in this case, is a list, right? Because there might be some other type contained in the list, which like might yield us another list, which we can then like use to do the nested thing. So so what we can do is, rather than, so where is the right place?
We want to
Where
know
do
the
we-
result of flattening the A is itself a list. That's what we want to know.
Yeah, so basically
Which for
where
maybe
we are
happens to be
making
yes.
the decision procedure here, we are like calling isList on A, but what we actually want is we want to know whether
Right.
isList of flatten of A.
Flattened, right?
Flattened of A, yeah. And then of course I have to change the call here and also here.
Yeah,
But the
so
rest
now we
is the
really are
same.
going beyond what we can do with overlapping instances.
Yeah. But the rest actually stays exactly the same, and I can run my example again. Oh, and I'm getting an error. That is unfortunately counterintuitive, and even a difficult one about non-injective type families. Why is that? Oh, it's probably, is that really just because I use...
Oh, maybe.
Is that, no, I don't think so. Is that? Yes. Oh, no instance for flatten. Oh, sorry. Am I? No instance of flatten prime true of list of maybe. Bool.
Do you still need the instance for list of A and list of A, even though you've... Are those two instances still the right ones?
I don't have an instance for flatten true.
Which you don't, right? Like the result, that instance is only for list of lists, but we don't really care anymore if the other
Right, okay, yeah, no, because I didn't do this step where I don't actually, I don't really need, just like I made the change, this is actually a good point, just like I made the change on the instance for show, where I said like, okay, you don't really need to have on the right-hand side this anymore. That's true. We can basically...
In fact, it's just wrong now.
Now it is actually just wrong, yeah. But, we can just remove this. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course I have to change the call here and also here. And then of course and probably here as well. Yeah. Okay. Sorry. Yeah. That was the missing ingredient. Yeah. I didn't. Yeah. I originally was planning to do the simplification step in between, and because I forgot about that, I now needed to make it. Yeah. But exactly. I mean, I think this illustrates nicely that we can do more interesting things, right? Once you're moving to this approach with using a decision procedure, you can replace that with more complicated logic that is not simply the specificity order of instances. And other examples arise if you have multi-parameter type classes, or if you have, say, if you wanted to like add cases to flatten for pairs or triples or something like that, and have sort of perhaps remove unit types from pairs or triples, and then we get instances such as, I don't know, where we have a flatten for something like a unit and a flatten for a and a unit, and with overlapping instances, these two are none of these two are more specific than the other, right? So if you wanted to apply something like this to a situation where you suddenly have a pair of two units, then also with overlapping instances, these two don't work. And then you either need to add yet more instances, or you need to move to incoherent instances. And incoherent instances are really unpredictable. Or you just use a type family that computes things fully deterministically, and you don't get into all this trouble. Yeah, I guess that is basically all I wanted to say.
Yeah, there are no questions. It's probably worth saying that while if overlapping instances work for you, it's probably okay, modulo some of the comments that we made at the start of the episode. Some people
I still use them. Yeah, I still use them. I mean, it's not something where I would say you should always like rewrite all your overlapping instances into this, but it can be a very useful technique if you're running into something where overlapping instances get in the way, or where you feel like you might even need to jump to incoherent instances or something like that. You should consider this technique and know that it is available, and perhaps it solves your problem.
Yeah, and the other thing I wanted to mention, and now there are two questions actually while you were explaining this.
Okay.
The other thing is that overlapping is usually fine with some asterisks, but incoherence is a whole different thing, right? I would say incoherences should probably be avoided.
Yeah, so I should perhaps then briefly mention why that is. So the idea with incoherent instances is that basically you're telling GHC that if that instance matches, it can pick it, even like regardless of whether there are other instances that might also match or not, right? So in a situation where you have multiple matching instances that do different things, that's actually already a problem, because then you essentially get non-deterministic behavior because you don't know which of the two GHC will pick.
Right.
And
yeah. Anyway, so there's a question from Pi. Can the original problem with the overlapping instances in different modules be avoided by avoiding overrun instances entirely? And I think the answer is probably yes, right? I mean, the problem was that we had one instance for a list in one place, another for another place.
I'm not sure. I mean, I my feeling is not, although I'm not sure whether I have a good example, because an orphan instance is only an orphan instance if neither the class nor the data type are defined there. But you could very well have a situation where the special case that you want to give in a different module involves like sort of like a list of an element type, right?
Yeah, exactly.
That is only defined in that module, and then it's not an orphan instance, and the same.
Yeah, list of my t of key would. Yeah, you're right. Yeah,
and then the same problem still applies.
And the final question from Christopher: how hard would this type family generation be to automate with template Haskell?
Exercise left to the viewer, I would say. No, I think not. I don't see a good reason why it couldn't be done. But as many things with template Haskell, it is perhaps we should do an episode on template Haskell sooner or later, but this is one of those things where you'll have to do a certain amount of syntactic analysis because you have to define a new type class with an extra argument and this and this and this. And it's not particularly elegant or nice to write this kind of program. I think once you have written it and once it works, and if a new GHC release doesn't change the API and breaks it, I think under all these circumstances, then it saves you a lot of work and is actually possibly automatable. But
that said, though, when I use
also the question is from what?
Right.
From what? Yeah, I mean, like the bigger question here is from what, right? You need an input, and you don't want the original instance. So I guess you could use the original instances as an input, and they would then not become part of your program, and it would just rewrite this. But then you're doing the whole thing and introducing the type family to make the order and the resolution more explicit. If you don't see that anymore, if that's hidden behind the template Haskell program, then do you really gain anything? I'm not so sure. I'm not entirely convinced. But I think if it's simply a question of can you do it, I think, yeah, there is probably a way that you can do it. But sorry, Etzko, I interrupted you. You wanted to say something.
I was just going to say that in the cases where I use this technique, and I use this technique relatively often, the type families tend to be usually interesting, right? They're more than just resolving something that would otherwise be done by overloading instances. Like, for example, like what Anders showed here at the very end with like the reasoning on the flattened type. And that's not something that you're writing a program, right? There's explicit logic in there that I guess can't really be generated.
Yeah.
So, yeah.
There's one more loose thing, one more loose end I actually wanted to tie because I forgot to say this. I mean, because I mentioned the show class. The show class in Haskell is actually not using overlapping instances either. It's using a different trick to avoid it by introducing a show list extra method that describes how to deal with showing a list of that particular type. And because show can work on arbitrary types and it has this extra method, then the instance for lists can just dispatch to that method. That is a different trick that sometimes works. And the reason that Haskell does this is that actually the show class predates the presence of overlapping instances. Like at the time the show class was introduced and this behavior was needed, overlapping instances didn't even exist. But unlike the trick with type families that I've showed, the one that is applied in the show class is not always applicable. You need a particular call pattern structure in your class in order to be able to apply it. It requires less overhead, but it is not as universal. Okay.
And also requires adding a new method for every different kind of overloading.
Yeah, okay, but I mean adding a new type class and so on. Yeah, but you're right. I mean adding a new method, that means in the original class means you have to go potentially through all the already existing instances, right, or add a default behavior. But yeah, I mean it has other disadvantages potentially. Yeah. Okay. I guess we should.
Yeah. Thanks for watching this episode of the Haskell Unfolder. It was a little bit longer than usual, but hopefully it was interesting. If you enjoyed it, please like and subscribe, and feel free to leave any comments below. We'll keep the chat open for like a few more minutes in case there's any questions now, and otherwise just leave them in the comments below the video, and hope to see you all soon.